Okay, here's an example on finding a probability. Suppose that the probability that you miss your alarm in the morning is given by 0.014, and suppose we have a 5-day work week for the next 2 weeks, and we'd like to know the following probabilities. A, that you miss the alarm on exactly 2 days, and B, what's the probability that you miss the alarm on at most 4 days, and what's the probability that you miss the alarm on at least 3 days. Now, if we make certain assumptions that one day is independent of every other day, so if you assume that days are independent, then we have n, the number of days, to be 10. So we have 10 work days in 2 weeks. We have 5-day work weeks, and these are nothing but the number of childs and on each day you either miss your alarm or you don't miss your alarm. So missing your alarm would be your success event, and that's that you don't miss the alarm would be the failure event. And we know the probability of the success event, P, it's given in the problem as 0.014, and under these assumptions that we have, we can actually use a binomial distribution to find these probabilities. So if you look at A, and before we get to the problem, let's define x to be the number of days you miss the alarm. Well, the number of days you miss the alarm is nothing but the number of success events. Now, we'd like to know the probability that you miss the alarm on exactly 2 days. You miss alarm Now, if I transform that to a literal expression in terms of x, I could write it as probability x is equal to 2. Well, the moment you see equal to, that should indicate that the probability that we are finding is an exact probability. And if you are finding an exact probability, we make use of what we call a probability density function, or PDF in short. So I know that I'm looking for a probability, and I know that the probability is an exact probability, and I know that this particular problem can be solved using binomial. So immediately we can come to a conclusion that we can use a binomial PDF to find solution. I know n is 10, p is 0.014, and x is 2. Therefore, the probability of x equals 2 is nothing but binom PDF n p x, which would give me binom PDF 10 0.014, 2. I'm writing it out in the exact syntax of a TI calculator. Now, on the calculator, if we press second VAS, that'll give me a set of distributions of user-defined functions. So if I scroll down, I would find Binomial PDF in option 0. So I press that and enter the parameters in the same order. The order is very, very important. So I have 10 followed by 0.014 followed by 2. Press enter and the answer is 0.00787, and if I want to retain 4 decimals I could round it and write it as 0.0079 approximately, which is nothing but 0.79%. So the probability that you would miss your alarm on exactly 2 days, it's only 0.79%. It's very, very small. How do we do the other problems? So in part B, we had the probability that you miss alarm on at most I believe it was 4 days, and if I want to transform this to a literal expression, I could write it as probability x is less than or equal to 4. At most would mean less than or equal to. Now if x is less than or equal to 4, then we have several possibilities. So we would have probability that x is 0, or, and or means union, x is equal to 1, or x is equal to 2, or x is equal to 3, or x is equal to 4. And since all of these individual events are disjoint, we can split it up and write it as probability x is equal to 0 plus the probability of x is equal to 1 plus the probability of x is equal to 2 plus the probability of x is equal to 3 plus the probability of x is equal to 4. Then I could use Binomial PDF for each of those, because each probability is an exact probability, and I could write it as 10 0.014, 0 plus the second term plus the third term all the way up to the last term. There is nothing wrong in doing it this way. However, since we are looking for an at most probability, at most, at least, greater than, less than, all of them fall under cumulative probabilities. So at most events, at least events, greater than events, and less than events, all of them are not exact events, they are actually cumulative events. They are cumulative events because, for instance, in this particular problem we have x less than or equal to 4. I started at 0 and I'm adding everything up to 4. I am accumulating up to 4. So I wrote it in this way, and I apply Binomial PDF for each of those terms, and I add all of those 5 probabilities. Now you could do it this way, but it's complicated. However, if you realize that this is a cumulative event, because at most is a cumulative event, then we don't have to use the PDF formula or function. Rather, we could just use a CDF function. So probability of x less than or equal to 4, instead of a PDF, I'll just use a Binomial CDF. NPX. What does CDF stand for? CDF stands for Cumulative Distribution Function. So the function would add all probabilities starting at 0 all the way up to 4. Instead of adding 5 terms individually, you're just adding everything together using one single function. And the answer this time would just be binom CDF 10, comma p, which is 0.014, comma x is 4 in this problem. So on a calculator, all we have to do is press second distribution again, scroll down to binom CDF, not a PDF, we have to use a CDF, press enter and press 10, comma 0.014, comma 4, and that answer turns out to be 0.99999, so which is approximately equal to 1. So that is a 99.99% chance that you will miss an alarm in at most 4 days in a 10-day work week. Could I have done it the other way? In other words, could I have done the same problem using the approach that we had initially? So I have binom PDF for the first and binom PDF for the second day, exactly 1 day, binom PDF that you missed the alarm on exactly 2 days, exactly 3 days, and exactly 4 days. Of course you could do it that way. Let me show you how we could get the same answer but actually doing it the hard way. So probability x less than or equal to 4 would mean binom PDF 10, 0.014, 0 plus ... up to binom PDF 10, 0.014, 4. Now I'm going to type each of those on the calculator. This might take some time. So second bars, first up I have to press option 0. I enter 10, 0.014, 4 plus binom PDF again. Second bars, binom PDF 10.014, 1 this time, because I'm starting at 4 and I'm starting at 0 and I'm adding everything up to 4, plus the next term. Repeat the process again. I am at 2 now, so 10.014, 2 plus the next term, .014, 3 plus the last term. Enter. Looks like I missed a term. I made a mistake in the very first term. Let's see. I'm going to redo this. If you observe, I started at 4 instead of a 0. So I start at 0 because the first term is a 0, and 1, 2, 3, and 4. Now press enter, and my answer is the same. I get 0.9999. So of course you could do it this way, but imagine you have to type in a lot of imagine that it's a lot of work for us to type in every single term, call binomial PDF each and every term, but binom CDF does the same task in less time. So using a binom CDF is the smart way for a cumulative event, instead of using a Binomial PDF. So let's see if we can do the next problem using the Binomial CDF. So we have probability that you miss your alarm on at least 3 days. Well, if I change this to a mathematical expression, x is the number of days I missed, x has to be greater than or equal to 3. Well, greater than or equal to 3 is a cumulative event. This is not an exact event. This is a cumulative event. So I must use a CDF right away. So keep in mind that you can't use a CDF function directly in this particular problem, because, let me write it as a note, CDF is used, or it always gives the probability of less than or equal to something. So CDF function, you can use it directly if you can have it, if you have the event as a less than or equal to event. But in this case, we don't have a less than or equal to event, rather than we have a greater than or equal to event. So we have to transform the greater than or equal to a less than or equal to without changing the logic of the statement. Well, if you used the complementary rule, the complement of greater than or equal to 3 is x less than 3. Still, I don't have a less than or equal to. This is a less than. But if we think about it, less than 3 means less than or equal to 2. So you can rewrite this as 1 minus the probability of x less than or equal to 2. Why is that? Well, let's write it on the side over here. So you missed it on 0 days, you missed your alarm on 1 day, you missed your alarm on 2 days, you missed your alarm on 3 days, 4 days, all the way up to 10 days. Now, greater than or equal to would mean 3 up to 10. What is the complement of this? The complement is nothing but the other side of the bracket. So the complement is this part right here. So the possibilities are x is 0, or x is 1, or x is 2. In other words, you did not miss your alarm on any given day in the 10-day period, or you missed the alarm on exactly 1 day, or you missed the alarm on exactly 2 days. So this is nothing but less than or equal to 2. So the cumulative event greater than or equal to can be rewritten in this form so that I have a less than or equal to instead. Now I have a less than or equal to event here, so I could write it as Binomial CDF. N is 10, P is 0.014, and X is 2, which can be done using a calculator right away. So let's look on the left hand side, press 1, let's clear the screen. We have 1 minus second pass, scroll down to Binomial CDF, 10, 0.014, 2, close paren, enter. And the answer is 3.0587. Now I can round it and write it this way, 3.059 e negative 4, and again that is the scientific notation, which means 0.003059. It's a very, very small probability that you miss your alarm on 3 or more days. So it's unlikely that you will miss this alarm on 3 or more days in a 10-day work week. So what we have seen is a CDF function. Sorry about that. What we have seen is a CDF function, and the CDF function, it is used anytime you have a cumulative event, and the PDF function is used when you have an exact event or you're trying to find an exact probability. So use a PDF for exact probabilities and a CDF for cumulative probabilities, and both of them can be done for a binomial problem using a TI calculator.